Good day, everyone. In our previous studies on this course, we have discussed the system of the linear equations. We have looked at the homogeneous system of equations and the non-homogeneous systems of the linear equations and the method of solutions. We have talked about the determinant method, which is what we call the determinant method, that is Cramer's rule, what we call Cramer's rule. We have also looked at the method of solving a system of equation using a matrix inversion. We also look at the method of the systematic eliminations. We have talk about the Gaussian eliminations and Jacobi methods. So on this study today, we are looking at the study section 3, titled linear mapping. We are looking at linear transformations. At the end of this course, you should be able to define what a mapping is, what are the linearity of a mapping, the transformations. You should be able to define the image and the range of the mapping. So we shall continue with the studies. We are looking at linear transformation. But before then, you want to look at what is a function. What do you mean by a function? When you are talking of a function, what does it mean? A function is a rule. We call that rule f. We denote it as f, that associates with each element in a set A, one and only one element in a set B. That is, you are talking of two things now. You are talking of two sets, set A and set B. So the rule that joins the two sets together is what we call a function. If f associates the element small letter a in capital letter A, that is, that your small letter a is a member of A, capital A, with element B in capital B. What does that mean? It's saying that small b is a member of the capital B, that is an element from the whole set B. Then B is equal to f of A. That is, we have defined the function there. B is equal to f of A. That is, a function defined from A to B. The values of B is what we call the image. Note that the values of B is what we call the image of A under F. Is the image of A under F. That your A, the element you get from that set A. So that is the image. B is the image of A under F. The set A is called the domain. So your set A is called the domain of F. The set B is called the codomain. So we have at the right hand side we have the domain. At the left hand side you have your domain. Then at your right hand side you have your codomain. So the codomain now is your B and the domain is your A. The subset of B consisting of all the images of A under F is called the range. The subset of B, I repeat, the subset of B consisting of all the images of A, under F is called the range of F. So we have talked about three things now. We have talked about the domain, the codomain, the range, and the image. So talk about four things. So your image, what is your image now? What is codomain? What is domain? And what are the range? So you should note all those things. They are very important. The value of B is called the image of A under F. The set A is called the domain of F. Set A is called the domain of F. And the set B is called the codomain of F. The subset of B, consisting of all the images of A under F, is the range of F. If A and B are set of real numbers, then F is called the real value functions of a real variable. If the domain of F is the whole real number of dimension n, and the codomain is real number in dimension n, A, F, and n may possibly be the same. That is, you can have the range and the domain and the codomain being of the same dimension, be of the same dimension. Then F is called the map or the transformation from n, from the real number of dimension n to real number of dimension n. That is, F is a function such as a real number n of dimension n mapped with a real number of dimension n. If n is equal to n, then the transformation F such that real number dimension n goes to real number of dimension n is called an operator on the real numbers of dimension n. That is, we are saying that the dimensions of the set, that is of the matrix we are talking about, may be the same. So that is what we are trying to explain here. Let's look at example to further explain what we mean. A function f defined by f of x is given as s squared. Is given as s squared is a real value function of a real variable. F is an operator on R. F is an operator. That operator is talking about the relationship that is there. Since F takes R to R, that is, F is a function defined from R to R. The equation given by y equals the vector y1, y2 is equal to 1, 2, then 2 minus 1 of x1, x2 is a mapping from a set of vector x in R squared. That is, the dimensions of matrix we are talking about here is 2 to the set of the vector y in R squared. That is, we want to define the function from y to x. So we have the domain, we have the codomain. Here, the x now is a two-dimensional. It's in two-dimensional matrix because we are having it as 2 by 2 matrix. We have 2 rows and 2 columns. So this one is defined a function as a mapping from a set of the vector x in R square to the set of the vector y and I square. That means you are going to have your y to be 2 and your x to be 2. So the next one we look at the linear mapping. Linear mapping. Let F be a set. Let F be a mapping from a vector space V, and let alpha be a member of a field. Is a scalar where your F is a field. F is a field. The mapping is linear if and only if for any Vi, Vj, members of V, that is your Ij, takes values from 1, 2, 0, 1, 2, and so on. Then you have the first condition. When you are defining a linear mapping, there are two things to test for to ascertain that that particular mapping is a linear or not linear. The first condition is that f of vi plus v, f of vi plus vj must equal to f of vi plus f of vj. That is, you must be able to establish that your right hand side is equivalent to your left hand side. When you have the vectors together, you must have the same thing as when you have them separately. If they are the same, that is the first condition. Then the second condition, you have a scalar, you multiply by a field. So f of alpha vi is equivalent to alpha of f of vi. That is, if these two conditions can be satisfied on a vector, then you conclude that that particular mapping is a linear mapping. Note, the mapping from the set N of all real square matrices to the set of all real numbers defined by det A is equivalent to B. You know what your B is. They are the codomain. The determinant of A is equal to B. Then A is a member of a matrix belonging to a matrix. A belongs to a matrix. Then B belongs to a real number. It's not linear. We want to check this one out. We want to check this fact out. We have to check out that the mapping from the set N, you know set N is a set, it's a matrix, it's a square matrix of a set of real numbers, whereby the determinant is equal to B. And that your A is the members of the square matrix, and B is also a members of the real number. We want to check that this one is not linear. How do we find out that? So using your condition, two conditions for a matrix, for a mapping to be linear, there are two conditions that must be satisfied. So we want to test, we want to establish that through these two conditions. And here we have been given our A to be a 2 by 2 matrix, which is A equals 1, 2, then 2 minus 1. And your B is equals to 1, 2, then 2 minus 1. You can see your A, you can see your B. Show that the mapping defined by Roman figure 1, delta A, that is the determinant of A, is equals B. And A belonging to a matrix, where B belonging to matrix is not linear. Then 2, f of A is equals to the transpose of A. We want to establish that that one is also linear. How do we go about this? Let's check it out. Linearity of matrix mapping. We have known the two conditions for a matrix to be mapping, to be linear, for a linear matrix to be linear. There are two conditions. You find the addition together and separately, they are equal. Okay. That's the first condition. And the second condition, you also establish that based on the data you have been given here. So we have been given our matrix A to be this and matrix B to be this. See that they are the same. Matrix A and B are the same. So the first thing for us to do is to find the determinant of A. How do you find the determinant of A? That is, you cross multiply. When you cross multiply this, you have 1 multiplied by minus 1, which is minus 1, minus 2 times 2, which is what? Is 4. So we have minus 1 minus 5, which will give us minus 1 minus 4, which will give us minus 5. So you have known the determinant of A now. So the next thing, find the determinant of B, which is also the same thing. So the next thing for you to do, you are finding the addition of the two now. So add matrix A to matrix B. Add matrix A to matrix B. So you will have 2, 4, 4 minus 2. So that is the addition. So from there you find the determinant of that also. So now compare the results, whether they are the same or not. So that will give you whether it is linear or not linear. If they are the same, that means they are linear. If they are not, that means it's not linear. So we want to check if the mapping C of A is equal to that A is linear. Recall, a function T is linear if it satisfies the two conditions. That is, T of A plus B is equal to T of A plus T of B. Then the second condition is T of CA is equal to C of T of A for any scalar C. Here, our scalar here is C. From the definition, the scalar there is alpha. So you can use any letter of the alphabet. It's just to define, it's just for you to mention that it's a scalar. So if it's a scalar, you are talking about a constant value. So, and this C here denotes your determinant. This C here denotes your determinant. So when you find out that as I explained earlier on, you have your det A to be minus 5 and your det B to be minus 5 also. When you have your matrix A plus matrix B, you have this. Then when you find the determinant of the additions of matrix A and B, you have minus 20. Because you are going to have, when you cross multiply that matrix, the addition of the two matrices, you will have 2 multiplied by minus 2 minus 4 multiplied by 4. So it will give you minus 4 minus 16, which is minus 20. So the additions of the determinant of the additions of two matrices is given as minus 20. And when you find the determinant separately, you will have minus 5 and minus 5 in the second one. So let's establish that now. The determinant of A plus B is minus 20. Then the determinant of A plus determinant of B is given as minus 10. So since minus 20s are not equal to minus 10, additivity fails. That is, the additivity conditions fail in that particular problem. And you conclude that this, so far the condition is not satisfied, it means that it is not linear. If it is satisfied, if the right hand side is equal to the left hand side, that is the determinant of the two matrices is equal to when you find the determinant separately and you add together. If they are the same, it's linear. But if they are not, that means it's not linear. So on this particular problem, it is not linear because the condition was not satisfied here. So the next one is to find out that the mapping is linear. That is when you have the determinant of A equal to the transpose of A. So we want to check that one out. Checking the linearity of this particular second condition. Let A and B be any two matrices of 2 by 2, that is of order 2, and C be the scalar. The determinant of A plus B is equal to A plus B transpose, which is also the same thing as A transpose plus B transpose, which is determinant of A plus determinant of B. Then the second aspect, you can check this one out using those values that you have here. Insert the values and find the transpose. Now to find the transpose, change the row to the column, then you get your transpose. So establish that from what you have, from the matrix given to you, you will see that this one is true. So the second condition is the determinant of CA is equal to the transpose of CA, which is the same thing as C multiplied by A transpose, and is also equal to the determinant C multiplied by the determinant of A. As you know, your C is a constant value, which is a scalar. Both property of linearity are satisfied. In finding the determinant of A equals to the transpose of A, these two conditions for linearity was satisfied here. So that makes us to conclude that the determinant of A is equal to the transpose of A. So far these conditions are satisfied, it is a linear mapping for this particular problem. So you find that you read further on this. So get matrices. Go into your exercises that you have in your course and in your study sessions and in the materials. Practice all the examples you have here to ascertain whether the properties are satisfied of the problems given to you. You test the two conditions. So if they are satisfied, it is linear. If they are not, it is not linear. If one is satisfied and the other is not satisfied, that means the condition is not met on that area. So you will conclude with the results you have gotten. So the next one is you have here is the linear transformation. We have talked about linear mapping. So we want to look at the linear transformation. Consider the real value functions of n real variable defined as this. This is the real value function v equals f1 of x1, x2 up to xn. Then we have your v2 to be equals to f2 of x1, x2 up to xn. And you continue that way, you also have your vn equals to fn of x1, x2 up to xn. the m equation, that is, we have the numbers of m equations, assign a unique point. The m equations assign a unique point v1, v2, v3, and so on up to vn in half n, that is, in a real numbers of m dimension. So each point v1, v2 up to vn in Rn, that is, in a real numbers of dimension n. This assignment defines a transformation. This assignment is defining a transformation for a real number of dimension 2 to dimension 3, that is dimension n to dimension n. You know, you are having your v1, v2 up to vn, and you are having your x from x1, x2 to xn. So let the transformation be denoted by c. So we want to assume that the transformation is denoted by c. Then we have c defined as a real r raised to power n to r raised to power n. That is a real number of dimension n to a real numbers of dimension n, and it's given as c of x1, x2 up to xn, which is given to be equal to the v1, v2 up to vn. Let's look at this example now to further explain that what we are talking about. The system of equations given by this v1 is equal to x1 plus x2, and your v2 is equal to 3x1 x2, and your v3 is given as x1 squared plus x2 squared. Define a transformation. Define a transformation c from r raised to power 2 to r raised to power 3. What are we saying here? R raised to power 2 to r raised to power 3. The image that we have is 2, and the domain that you have is what? Is 3. That is, we have v1, v2, v3. While the images that is producing now is producing x1, x2. So the image of points x1, x2 is c of x1, x2, which is equal to, that is, we have two things now. The images are 2. We have x1 and x2. So the c of x1 and x2 is given as the first one, the second one, and the third one. That is the first v, the second v, and the third v, which is v1, v2, and v3. And the v1 is given as x1 plus x2. Then the v2 is given as 3x1, x2. Then the v3 is given as x1 squared plus x2 squared. The transformation Rn, that is R dimension n to R dimension n, is called a linear transformation. It's a linear transformation or a linear operator. This one is a linear operator if your n is equal to n. If the equations in one is satisfied, then it is a linear transformation. Generally, the linear transformation T, defined as the real numbers of dimension n to real numbers of dimension n, is of the form V equals AX, where your V is defined as a vector. So vector V is defined as V1, V2, up to Vn. And your A is given as a matrix, which is a n by n matrix. And your S is a vector from x1, x2 up to xn. You find out this now. We want you to establish this, that this particular example is a linear transformation. So you combine them, you establish that for us. That this is a linear transformation. The equation V1 given as 2x1 minus 3x2 plus x3 minus 5x4, that is the first equation. Then the second one, V2, is given as 4x1 plus x2 minus 2x3 plus 4x4. Then the third one is V3 equals to 5x1 minus x2 plus 4x3 is a linear transformation T to R4, that is R is the real numbers of dimension 4 to real numbers of dimension 3. That your 3 is your V, your V1, V2, and V3, while your 4 is your x1, x2, x3, and x4. So this one is a linear matrix because we are going to have the image as a V1, V2, V3, V4, which is a linear transformation.